When the only forces acting on a system are conservative, then what we can do to a system is apply what we call conservation of energy. And conservation of energy is simply defined as in a system before an event takes place and then after the event takes place, the total change in the kinetic energy plus the total change in the potential energy is zero. What this means is that no energy is entering the system, nor is any energy leaving the system. Okay, so when I have conservative forces, then things like friction are not involved in dissipating energy out of my system. I can actually include friction in my system to use energy conservation, but at the end of the day, for most practical purposes, energy conservation is limited to the conservative forces. So what this means is that energy can change shape or form between these two, okay? So energy can transform from potential to kinetic and then from kinetic to potential as a system is evolving or moving, but the total sum of the changes in kinetic and potential cannot change. So the total change in energy is zero. Another way of saying this that I like to write it down is that the total energy initially in the system is equivalent to the total energy present in the system at the end of the process, whatever that process may be. Another way to break this equation down, and you get the same thing if you break this up into this result, because this is just your final kinetic energy minus your initial. This is just your final potential minus your initial. And so essentially, if I want to rearrange this equation into a form like this, I get this. My kinetic energy initially present in my system plus my potential energy initially present in my system is equal to the kinetic energy present at the end of the system plus the potential energy present finally at the end of the system. Now, why is this such a powerful statement? Let's do a very simple example. Okay. Now, let's go back to the brick that we had, and we lifted it from point A up to point B. And now let's say we're going to release it. So we're going to let it fall, okay? So I want to know if it falls into the ground, okay? The basic question is this: how much energy is the brick going to be putting into the ground? Now, we really don't have things called energy meters, but what can I measure as the object is about to hit the ground? I can measure its velocity. So what I want to know is what is the velocity as the object hits the ground. Now, we already know how to do this. We can use Newton's methods. We know that the acceleration downward is going to equal g, and so then I can use one of the kinematic equations. We can say v final squared is equal to v initial squared plus 2g delta y, and I'm going to keep a plus here even though g is downward and negative. Delta y would also be negative, and so those two cancel out. I get this, and if it's released from rest, then vi is 0, so I get vf squared equals 2g delta y, and vf is equal to the square root of 2g delta y. Now, that's a pretty simple result, just a few steps to get the final velocity. I can use conservation of energy to get this same result, and that's one reason why we have such high confidence in both Newton's laws and energy conservation, because they are consistent with one another. So let's see how it's done. So energy conservation would say that the energy initially present in the system must equal the energy finally present in the system. So my initial system, or not the initial system, the whole situation is the system, but my initial point in my system is when my brick is raised to this height B above point A. And so before the brick is released, it has potential energy mgh, where h is the difference between b and a. And so here I'm going to write down mgh. It has potential energy mgh initially present in the system. Before it falls, it's at rest, so it doesn't have any kinetic energy. Once it hits the ground, all of its potential energy has been expended and converted to kinetic energy, so I don't have any potential energy present after my object has fallen. And as it's going to collide with the ground, all of that potential energy has been converted to kinetic. And so we now start with this very rather simplistic equation, mgh is equal to 1/2 mv squared. Pardon me. And now I want to solve this equation for v. And so I can see that my masses cancel. I can multiply both sides by 2. So I'm going to get 2gh is equal to v squared. And this is identical to what we had before, because the difference between a and b is equal to the delta y that we used in the kinematic equation, and that's equal to the height that the brick has been raised. So 2gh is equal to 2g delta y in the previous way to do it. And then I just take the square root. And I can see that I get the exact same result using conservation of energy. Now, this is a example of where both Newton's methods, using the acceleration due to gravity, and the kinetic or the conservation of energy methods are roughly equivalently the same in length and difficulty. They're both fairly easy. So let's look at the inclined plane problem now. All right, let's look at the inclined plane problem. And let's show you the example of how to analyze the inclined plane problem using conservation of energy instead of Newton's laws. So if I have the inclined plane and I have a box, and again this is theta, and I have a box released from the top of the incline and it slides down, and let's say we're given the length of the incline, then I want, and we're going to say that the initial velocity is 0, it's released from rest, and I want to know what the velocity at the bottom of the incline is as it's sliding down. Now we're going to exclude friction for right now, okay? We're going to exclude friction for right now, but at the bottom of the incline, I want to know what the velocity is. And so how do I do it? Well, before, we would draw our free body diagram and state, well, the weight is down, the normal force is acting up this way, we have the component of gravity this way, we have a component of gravity this way, so this is mg sine theta, where this is also theta, this is mg cosine theta. And what we said was that it's this component of the acceleration moving it down the incline, so this is mg sine theta, and that is equal to the force of gravity that is pulling it down, so that's equal to the net force. So if F equals ma, then this is equal to mg sine theta, and therefore our acceleration is g sine theta. And so then we use the third kinematic equation again, where we release it from rest, so vi squared is 0, so this is just going to be 2 g sine theta times L. And so then v becomes the square root of 2g sine theta times L. Now, this is a fairly complicated free body diagram. It's one of the most complicated we've done, and if you're really going to truly do this problem from scratch, you have to follow all of these steps. Once you're very familiar with the inclined plane problem, you can just state that the acceleration is g sine theta, and then the steps fall out from there. But if you're really going to do the problem from scratch, the true way to do it using free body diagrams, F equals ma in both the horizontal and vertical directions. I didn't even set up F equals ma in the vertical direction in this case, because without friction, the normal force and mg cosine theta cancel out, and they really don't play a role in the final velocity down here. But now notice something, okay? First things first, I have this sine theta L term in here, right? And remember that the definition of sine theta is equal to, if I now look at my right triangle, and I'm going to get rid of the mg sine theta and the mg cosine theta, the height above the ground the box starts at is the height of the incline, right? And it is the opposite side of this angle. So sine theta is equal to h over L. And so L sine theta is equal to the height of the incline, okay? So that's going to be a key piece here. Now, how can I solve this problem using just energy, all right? So we'll keep this in the back pocket here. So we have that h is equal to L sine theta. And now we want to solve the problem using energy conservation. So to use energy conservation, we say that Ki plus Ui is equal to Kf plus Uf. And again, at the top of my system, there is no kinetic energy, so this term goes away, and I'm just left with my initial potential energy, the potential energy, gravitational potential energy the object has at the top of the incline. At the bottom of the system, all of the potential energy is gone, so this is now 0, and I'm left with my potential energy at the beginning is equal to the kinetic energy at the bottom. Now, this is the form that we've seen both of our examples take. That's not generally going to be the case. You can actually have potential energy down here depending on how the problem is set up. Let's say that the box doesn't slide all the way down, but maybe halfway down, and you want to know what the speed is right here. In that case, you still have potential energy, so this is not always going to be 0. Or likewise, if you give the box a shove down the incline, then your initial kinetic energy isn't always going to be 0. But anytime the object is released from rest, it will be. And so now we have mgh, which is the initial potential energy, is equal to 1/2 mv squared. And my m's cancel out again, and now v squared is equal to 2gh. And now v is equal to the square root of 2gh, but h is equal to L sine theta, so this is identical to what we had before using Newton's laws. But notice how simple this process is now. I don't have to worry about the angle. I don't have to worry about what angle the incline is. As long as I know what my height here is, that's all that matters. So what this equation is saying and what energy conservation is implying is that it doesn't matter if an object is sliding down an incline, if it is at a height h above the ground, when it reaches the ground, it will be going this velocity, 2gh. Now, if I have a very steep incline, obviously a steep incline of height h, obviously the box is going to get down to the ground faster. But these two inclines, I guess it will make sense what I'm saying with a diagram here. What I'm saying is this. Let's say that I have a very non-steep incline of some height h, and then I have a very steep incline of the same height, right? And I have identical boxes on both inclines. Obviously, this box has a much shorter path to travel, but both inclines are at the same height above the ground, and so even though this box is going to take a shorter amount of time than this box, they will both be going the same speed when they hit the ground, okay? So that's one way you can use energy conservation. Let's do one more example, and this time let's incorporate springs.